Good day guys, we'll be discussing the categories of colligative properties, which is the boiling point elevation and the freezing point depression. At any given temperature, vapor pressure of solution is always lower than the pure liquid. I already said this in our previous class. That is, the normal boiling point of a liquid is the temperature at which the vapor pressure is equals to the atmospheric pressure, 1 atm. And at normal boiling point of pure liquid, the vapor pressure of that solution will be less than 1 atm. That is a solvent that has been mixed with a solute. Now, since it is less than 1 atm, a higher temperature will be needed to raise the vapor pressure to 1 atm. That is more than the normal boiling point. So we could say that what the boiling point of the solution is higher than that of pure liquid, because it will need a higher temperature to raise it for it to be equivalent to 1 atmosphere for the solution. Now that means that instead of it to boil at 100 degrees Celsius, the solute that is there will not allow it to do that. So also the temperature do increases by the amount of solute that you put into it. That is, the amount of moles of solute that you keep adding into it will keep evolving and tending to what? To need much more temperature for it to what? To heat or get to the 1 atmosphere. So we could say that what? The increase in the boiling point relative to that of the pure solvent, that's the change in the what? In the boiling point temperature, is directly proportional to the number of solute particles per mole of the solvent molecules. Now you have to note something here, that molality expresses the number of moles of solute per 1000 gram. Do not forget that this is also in our previous video. For those who are just new, you can check out our previous video under colligative properties. They are all there. Now it says that what? It represents the number of what? The moles of solute per 1000 gram of solvent, which represents a fixed number of mole of that particular solvent. So we could easily see that what? The change in the boiling point temperature varies directly as the what? As the molality. And for every variation, there is a constant of proportionality, which brought about the boiling point. We call it the molar point elevation constant, Kb. So the molar point elevation constant usually depends only on the solvent. For easy clarification, I don't like to write the formula as the change in the boiling point of the temperature is equals to the I. This I is the number of molecules that dissociate into the water. So we need to check out what we call Van Hoff's factor to understand that I better, because you see, ordinary that formula could not really help you to understand some things better. So that I stands for the amount of moles, because some electrolytes can dissociate into the water and we need to put their values there. That was why I said that it depends on the mole. That's the number of molecule that dissociates into the water and not the type of dissolved particles. So for us to know the total of moles that dissociates into the water, we need to visit Van Hoff factor. Van Hoff factors can be used to denote the number of ions that a compound used to dissociate into by the formula unit. So for an electrolyte, the Van Hoff factor is always greater than 1. That electrolyte dissociates into values greater than 1. Yeah, for an electrolyte. While a non-electrolyte, the value for the Van Hoff factor is always equals to just 1. Looking at sodium chloride, you have sodium ion and chlorine ion, making it a 2 dissociation of molecules of ion. Potassium bromide, the same thing. Calcium chloride, you have Ca2 positive and Cl negative, which gives it a 3 dissociation. Sucrose is a non-electrolyte, so therefore the Van Hoff factor would be equals to 1. And we have acetic acid. Alright, so let's discuss about the freezing point depression. You see, when solute freezes, crystal of the pure solvent usually separate out. So the solid molecule are not normally soluble in the solid phase of that particular solvent. Now you see, when you see that aqueous solution they are usually partially frozen because of what? The solute that freezes won't be fully freezed. So that is why that solid that separates out is going to be almost always pure ice. That's at the surface. If you've got into ocean before, freezing in ocean, you would see that all the top would be pure ice, but beneath there is still water. So the freezing point of a solution is the temperature at which that first crystal of the solvent usually begin to form in what? In equilibrium with the solution. So the freezing point of solution is lower than that of ordinary pure liquid, which we all could testify to that. Now the decrease in the freezing point, that's the change in the freezing temperature, is going to be proportional to the what? To the molality of the particular solute. So the change in the freezing point temperature, that's the decrease, can be equals to the molality and times the molality freezing point depression constant. And I equated it as a negative I, which you all know that it is a Van 't Hoff factor. Why the negative is being included here is simply because the temperature, the value for the particular freezing point depression would decrease below 0 degrees Celsius, which is a negative temperature. So the freezing point depression usually explain why we use antifreeze for car and also why we use CaCl2 to melt ice on the road during winter. And these are some constants. The water has the boiling point constant and also same as some other solvents which you can see. So it has its freezing point constant and its boiling point constant. It is constant for the solvents. So whenever you are being introduced to them, you make sure you use its preferred boiling constant. Let's take a look at this problem. It says automobile antifreeze consists of ethylene glycol, which is a non-electrolyte. So therefore, that means our I will be equals to 1 without not thinking too far. So it says calculate the boiling point and freezing point of a 25 mass percent solution of ethylene glycol in water, which means 25 mass percent of solution of ethylene glycol in water shows us that out of what? 1000 grams, simply because molality is equals to the number of solute over the kilogram of solvent, a 1 kilogram. So which we could easily say that what? We all know that the 25% for ethylene glycol could equivalent to 250 gram. And since it is equivalent to 250 gram, we all know that what? The mass of percentage of water would be 75%, which would also be equivalent to 750 gram. And as we all know that our mass of water can't be in gram because we need it in kilogram for now. So therefore, we all know that if 1000 gram is equivalent to 1 kilogram of water, so therefore 750 gram would be equivalent to what? Then we cross multiply and do our little division and little arithmetic. So therefore the mass of the water in kilogram would be equals to what you can see, which is 0.75 kilogram. Then we look for the number of moles of the solute, which is ethylene glycol, and that will be equals to the mass of ethylene glycol, which is what? Our 250 over the molar mass, which you all know the molar mass of ethylene glycol already. We've been using it several times, which is 62. So that would be equals to 4.032. Then we find the molality. Here we have two different things. There's difference between finding the change in the temperature of the boiling and freezing point. If it is that what you are being asked for, you are just to apply the normal formula. But when you are being asked to find the particular solution temperature altogether, that means that after you've gotten the change in temperature, as you can see there, then you are going to proceed in finding the particular temperature for the total solution, which means you are just to add the temperature for the normal boiling point and the temperature for the normal freezing point plus the change in temperature for the boiling point and also plus the change in temperature for the freezing point. Then we are right there in the jackpot. So that is all about the freezing and boiling point, and I hope you all learn one or two things. Thank you.